All right, good morning. So yes, my name is Kristof Beyls. I work for ARM, and this morning I'm going to share some of my thoughts about compilers and security. So one of the views I have is compilers for a very, very long time has been all about correctly translating source code to your target assembly or whatever, and at the same time optimizing. And I've been observing, from my point of view of the world, somehow in the past couple of years as a third pillar now, it's called security. And so I'm going to talk a little bit more about that in this presentation. And so just to put that into a little bit of perspective, I try to put up a timeline on how have compilers evolved over time. Apparently, sometime in the early 50s, the first Fortran compiler was created. It was immediately an optimizing compiler. The aim was, let's make sure that this first compiler we built, it already optimizes better than what people write by assembly. So right from the start, it was all about optimizing. A little bit later, sometime in the 70s, roughly around the time I was born, there was the first iteration of the Dragon book. So probably by then, there was a lot of theory already on how do you build a compiler, how you make it correct, how you do lots of optimizations. A little bit later, 1984, Ken Thompson gets the Turing Award. In his thank you speech or acceptance speech, he demonstrates, hey, did you know that you can put a backdoor in your code generator and you can't even see it in source code and it will generate? So there's a first glimpse of security and compilers. There's a relationship there. I think another big event, looking in reverse, is this paper called Smashing the Stack for Fun and Profit. It really showed you, hey, this is how you do a stack smashing attack. And that's really where I think the whole arms race between attackers and defenders started on memory vulnerabilities. So a really big event. And of course, compilers had to start building in security hardening. So probably stack canaries with this command line option, fstack protector. It landed in GCC in 2005. Maybe that's the first really big popular security hardening feature in an open source compiler. And then lately, different open source compiler communities started setting up security groups, ways to be able to report, hey, there's a security issue here, but to be able to report it in confidence so the issue can be fixed before it becomes public knowledge. And so, from my point of view, that's roughly where security became a key aspect of doing compiler work. So if you look at this timeline, for some 75 years, it's been all about correctly translating and optimizing. And then just in the past couple of years, security also became a hot topic. And so looking at that, I think that as a compiler community at large, we're pretty good at doing correct translation and doing optimizations. We've had 75 years to learn how to do it. But security, my personal feel is we're still learning. We're still learning a lot. So with that general background, at least that's a perspective I have, and I don't know if you agree or not, you can let me know after the talk. So with that perspective, maybe let's dive a little bit deeper. So what are the kinds of security aspects that appear in toolchains? And again, I'm going to show based on my personal experience being part of one of these, of the LLVM security groups, seeing security issues come in, and also seeing all the security related stuff. So I think this is my current view of these are the kinds of aspects related to security you have in compilers. I'm sure this is incomplete, but it is a starting point. So first of all, open source compilers like LLVM, there are pieces of open source software, so everything related to security in open source applies to compilers. So for example, our runtime libraries, they're probably the most widely used libraries in the world, embedded into every piece of software there is out there. So any vulnerability there affects all of the software in the world. Of course, we also have everything related to open source supply chain security. But today, I'm not going to focus on that. That's for another talk, for someone else who knows more about that. There's also some code generation specific aspects to security in compilers. And so a first big category is compilers have features that help the software you built with that compiler to be able to have somewhat better security for whatever security means there. And so some of the features are about hardening features. Some of the features are about finding bugs in your programs like sanitizers and debugging tools. Maybe there's also a role for creating software bills of materials. I remember we had a talk last year or 2 years ago about how Clang could automatically create. This is exactly the software that went into your build, like exactly these source files. So I'm seeing some impressions that the creation of a software bill of material is going to get only more important in the future. And then, yes, supply chain attacks, like at least in theory, it's possible to put a backdoor in your compiler so that, hey, you're compiling some software and at the end, there's like a backdoor in the software you produce. So yeah, also an issue that exists. So I only have like 38 minutes left, so I'll be narrowing my focus again, just looking at security hardening features and toolchains for the rest of the presentation. So this is a chart that shows the kinds of security issues that we've received in the LLVM security group over the past 3 years. And the area in red represent issues related to there are gaps in security hardening in the compiler. Later this morning in a quick talk, I'm going to talk in a little bit more detail about the kinds of issues we've received there. But this is just to show, like, yes, we are receiving a significant number of issues related to security hardening features. And maybe not all of you are very familiar with security hardening features, so maybe I thought I'd put on the slide. These are the kinds of command line options that are security hardening features. So you have stack canaries, you've got branch protection features, you've got, well, let's not leave variables uninitialized, and so on and so on. Actually, if the link at the top from OpenSSF is a list of this is what is recommended, the kinds of security hardening things you should enable by default for all C and C++ software you build. It's actually all of the command line options on the slide and more. So you could say that both the security hardening features should get used to build all of the software in the world. So like the whole world depends on it. And both, like, we're getting quite a few issues with those security hardening features. Is there anything we can do to like improve the quality of the implementation there? So let's think, what could it be? What could possible root causes be of like the quality of implementation not being as high as it could be? From looking at the issues we've received, sometimes we see people saying, hey, I saw this code generated with a security hardening feature and I think it's wrong. And then, like, as part of the security group, we try to get the implementer involved, the person who designed the security hardening feature. And they said, like, no, it's working as expected. This is a known limitation of the security hardening feature. So one of the issues is the documentation for most hardening features is a little bit underspecified. It's a bit hand-wavy, so making the documentation more exact, this is exactly what you get from a particular feature, would help. Though sometimes we also see, oh no, yes, well, the compiler isn't doing what's promised in documentation. It should be working the other way, so that we actually have some gaps there. And my thinking so far of potentially the two main reasons for why there are bugs there is maybe a first reason could be that in general, compiler engineers don't have a great amount of background on security. I know, at least I didn't a few years ago, and I still don't, but I'm learning. And then the second thing is, what it turns out, it's hard to test whether you've correctly implemented the hardening feature. So first, a few things I've tried to do on learning about security stuff. So one thing I started 2 or 3 years ago together with a colleague of mine, Giorgia Covelli, is we thought, yes, we want to learn more about what should we know about security and compilers. We don't know. And we looked around and like there wasn't any book that really said it. Like you can find lots of papers demonstrating this specific exploit and this specific exploit, but how do you know like you've got your basics covered? And so we thought, okay, maybe the best way to learn ourselves is we'll just try to write about it, and then we'll very quickly discover, oh, we don't know about this and we need to study this a bit more. So this is an ongoing project. It's an open source project under the Creative Commons license. You can find this book at EuroRL on the top of the slide. I think probably it currently contains like half of the material that really should be there before it's complete, but probably it has the most important half. If you are interested to go and have a look, please, if you have any feedback, do share it with us. We want to make this book better, but we need more feedback. Of course, you can also just contribute easily yourself directly. It's under a very permissive license, so please do so. A second small thing I tried was something slightly different. In the book is a little bit theoretical. You read about these concepts. I also found that actually it's really useful to try and build an exploit yourself, like play the attacker, because then you recognize like, oh, this is how I could get in if you see a piece of code. And so to help with that a little bit, I thought, let's look back at that Smashing the Stack for Fun and Profits paper that started it all some 30 years ago now. And I made a hands-on tutorial. It's part of ARM Learning Paths. It's also fully open source under the Creative Commons license. And so basically what you do there in just like an hour or 2 hours, you have a number of command lines that you can copy paste to set up your experimental environment. And then it just leaves, so you get going, and then it lets you think for yourself, like exactly what do I need to do to like override this return address on the stack so I change the control flow of my program. So with a little bit of time investment in just 2 hours, you can build your own stack smashing stuff. I'm like, again, if I hear positive feedback, I might do a few more of these. And also it's an open source project. Everyone can contribute. Right, so with all of that said, like let's dive into like the core topic of this talk really, which is about security hardening features when we implement it. How can we test them? After thinking about it for a little bit, it turns out that like what are our standard testing practices that we use when we do correct translation or optimization? Our standard practices are, well, we have regression and unit tests, which really check like, did the exact assembly come out? Which is like a really good test, but it's just on a very small number of handwritten test cases. Then we also have larger test suites and benchmark suites where we just compile lots of code and we measure, does it produce the right output? Is it fast enough? But it does not test like, did we make this binary more resistant to attack? When you look around at what people implementing hardening features, sometimes what they do is they find like, I can't really test this very well, and they create their own ad hoc binary analyzer to check like the binary coming out, does it have all the properties that I hope it has? And so, for example, there's an LLVM blog post on that when I think it was Serge Galton implementing stack clash protection, explaining this what I did. I had to build my own ad hoc binary analyzer. So that's really good because it means the implementation is tested way better. But then, of course, it lands, and then every day there's 200 commits to LLVM. And so how do you know we don't have any regressions there? We don't. So I was wondering, could we create a binary analyzer that checks for all the properties that a hardening feature should get? And basically, if we had that, basically that category 2 test, the test suites, we could also check like, did we make the binary a little bit more resistant to attack? And so if we would have a binary analyzer like that, what could we use it for? So in compiler development, well, you could use it while you're implementing and check like, is it working? You could add a scanner like that to CI loops, pre-commit, post-commit, wherever, to make sure to detect the regressions. You could even like integrate it into a fuzzing setup, and like for example, check does a hardening still work correctly with non-default compiler options. By the way, the LLVM security group also has received reports saying, yes, the security hardening feature works, but I use this one non-default option and it breaks down. So it is a real thing. By the way, my colleague Oliver Stannard later today is also going to give a, raise your hand, Oliver. Is also going to give a quick talk on some of his work doing fuzzing with compiler, non-default compiler options and so on. So that's as part of compiler development, you could use a tool like this. I think in packaging or distro building, you could also use a tool like this, like you scan across a whole distribution. You could integrate into the distribution build process. It also turns out that like for some mitigations, there are like people implementing the mitigations by hand. There are some known gaps in a few places. You can't always apply all of the mitigations easily, and there are good reasons sometimes. But it's very undocumented. Like when I discovered, for example, a gap like that, I went to the implementer and said like, yeah, of course. And like, who knows about this? Well, me and the person who reviewed the code. And so there's another 8 billion people in the world who don't know about it. So it could be helpful to find where are those gaps and just document like, yeah, this is a known gap. And so a last use of a binary scanner like that, if you think about it, like security hardening, the more general thing you're looking for here is properties in the binary that don't show up while you're running the program, or that don't show up in the output of the running program. And do we have a few other things in compilers where we also have it? Yes, probably. One example I'm thinking of is like making sure that your frame chain or frame pointers are correct. Like if that's broken up, your program still runs and it still runs as fast and it still produces the expected output. But if you have, like, if you're sampling your program to get a profile, or you're missing some of the backtrace and you don't get that, so maybe for use case like that, it could also be useful. So I think a tool like this would have a lot of value. So do we have a tool like this? Well, I looked around and I didn't really think there was. Do we have experience in building binary analyzers? No, but like, how hard could it be? Let's see if I can build one. So I thought, okay, I'll start with a relatively easy one. This is one that I happen to know, pointer authentication or return instructions. I'll explain in the next few slides a little bit of background on what that is exactly. And then I also tried to implement the harder one, which is stack latch protection. And I thought up front, like maybe this is going to be harder because for that one, I really need to keep track of like every time the stack pointer changes, stack grows, and all access to the stack. So is it probably that's theoretically infeasible, but maybe practically just about doable? Let's see. Pac-ret hardening. So the assumed threat model typically is there's some memory vulnerability somewhere in this big binary you have, and somehow an attacker has controls some input to your program, and somehow they manage to override the memory location in your code. And we typically, like, there's protections in place to make sure that them just writing to memory, they cannot write instructions directly, and so they cannot inject code into your program. But what they typically can do is they can override a code pointer. And so if they can override a code pointer, like all of a sudden they control the control flow in your program. And quite often, like they can do interesting things, like if you can just diverge control flow to go to a system call and say like, open this network port. And so like, then the attacker can dial in from anywhere on the internet, has access to your machine. That's just one example of how they could work. And so overwriting a code pointer, when they overwrite a return address, so when you have a function call, instead of returning to like right after where your function was called, they jump to just some other location in your code and start taking over. That is called return-oriented programming, or ROP. And when they override some other code pointer, like a function code pointer or some other code pointer. That's typically called the jump-oriented programming. Now, in the ARM instruction set, there's an extension called pointer authentication. And really what it aims to do is to make it harder when an attacker overwrites a code pointer in memory. This extension tries to make it likely that it gets detected. And so how does that work? So in a 64-bit architecture, many of the bits are used to represent the address of where something lives. But then you still have quite a few bits left over that are not used. And so if you put some metadata in those bits, maybe you can make that use that for something else that's useful. And so in this extension, it's being used to put in a cryptographic hash of that address. And it's being computed in such a way that it would be hard for an attacker to compute a correct cryptographic hash. So basically, so what the extension does, it has a number of instructions that enable you to turn a raw pointer, so you just have the address bits, into a signed pointer where the upper bits have the cryptographic hash. They also have an authenticate instructions where basically what it checks like, is this a correct cryptographic hash for these address bits here? And if it's not, then it interrupts execution and goes into some signal handler. Maybe this is going into a little bit more detail than is needed for here, but basically what goes into the cryptographic hash, while the address goes in to compute that, there's like a secret key that's not in memory, but just on a special island in the chip that goes in, so the attacker can't get access to that. And then there's also something called a modifier. I'll show an example on the next slide to make sure that you just cannot read a pointer for, the attacker cannot read a validly signed pointer somewhere in the program and just override it somewhere else. So a little bit of code to try and make it a little bit more concrete. So assume you have a function call. That BL instruction is branch and link. That's how you do a function call on the AR64 instruction set. What it does, it will jump to somewhere else. And in one particular register, X30, a register on AR64, it will put in the address of the next instruction, where to return to. So it calls a function. Now this is, as you see it on the screen right now, this function is not protected by pac-ret hardening. So first instruction, it stores the return address and frame pointer on the stack. Maybe it calls some other functions. Maybe in that tree of functions that are being called there, the attacker has a gadget where they can start overwriting memory. Then that function returns. That LDP is load pair. It loads two registers. The return address, X30, it loads it back from memory. Maybe by that point in time, the attacker has overwritten memory, so it controls the content of X30. Then the return instruction executes, and at that point, hey, the attacker has taken over the control in your program. With pointer authentication, what happens? You put in, at the start of your function, a signing instruction. So this instruction really means sign the X30, where the return address lives, with the IA key and with modifier ESP, the stack pointer. So that puts the cryptographic hash in the upper bits. Next instruction puts it into memory. The attacker still overrides that address, but they get the cryptographic hash wrong because you cannot compute that offline. And then when it's loaded back from memory, the authentication instruction checks, cryptographic hash was wrong, gets detected, and maybe your program just crashes, but the attacker didn't take over your computer. So with that scheme, to implement in a static analyzer, what's the binary property to check for? Because compilers could they do optimizations and the code might not look exactly like on the slide. So what's the invariant to check for? The thing I came up with was, well, you have for every return instruction in your program, you look in your function back and you see, was there any instruction overwriting the link register? If there was, that should have been an authentication instruction, and otherwise this looks suspicious and it should be highlighted. Right, now that we know roughly the kind of property to scan for, let's go and look for a binary analysis framework where to implement it in. Over the past 2 years, I have been playing with this idea a little bit, and I tried a few different frameworks. But in the end, I ended up with trying to implement this in Bolt. And I think Bolt has quite a few good properties to do this in. So first of all, on the top of the screen, you see, like in blue, the 4 big blocks, steps that Bolt goes through while optimizing code. So it reads a binary, it reconstructs a control flow graph, and then to go and optimize, it reads some profile information, it does rewriting, writes it back out. And so the idea is for a binary scanner, well, we can reuse that reading a binary from disk, reconstructing a control flow graph, and then do binary analysis. Other good properties for Bolt for this is it works at the MC inst layer, which means like you still get an exact representation of the binary as it gets executed. It uses concepts that are familiar to LLVM developers. So in the same framework, when you're implementing a hardening feature, you can also start building your analyzer. Bolt is actually actively used by large corporations to do really important and valuable optimization work. So I've got some trust in Bolt, has a long, healthy life ahead, and it will keep on being maintained. For example, support for new instructions which come out every year will just be added as part of the optimization workflow. I don't need to do extra work for the binary analysis workflow. So some of that work on reading binaries, reconstructing control flow graphs, we can share that cost with the optimization use case. I thought, okay, to test this, I'll pick all of the libraries in a Fedora 39 distribution. It turns out that's about 250 million instructions in there, so probably that's a good enough test case for like building a prototype. And then, okay, let's start implementing this. First implementation, you run over it. I just see lots of reports, probably most false positives, errors in my implementation. So fix that, do another run. Okay, fewer false positives, do another run. And so iteratively improve the implementation. It makes use of the Bolt's built-in data flow analysis. There are a few issues that I had to work around where Bolt wasn't able to process every single binary in there. But I'm going to skip over the details there. I also got the question in the past, like, doesn't binary analysis take a huge amount of time? Well, at least for that prototype I built in, I thought it's totally fine. So this was running on like this laptop on a single core. It takes 10 minutes to scan all of the libraries in like a Fedora distribution with lots of packages installed. Runs at about roughly 500,000 instructions scanned per second. I think that's more than fast enough. Is it hard to implement? Well, maybe not the best measure, but like it's on the order of maybe 1,000 lines of code to implement the scanning algorithm. And yes, I also needed some boilerplate to like make a new tool. So what are the kinds of gadgets? So the prototype isn't fully finished yet, and there's still false positives, and there's more work that can be done there. But I think it's starting to show interesting results already, which is why I thought I'll present it here rather than wait another 6 months before I'm going to talk to the world about this. So about 2% of all the returns, the scanner says not protected. And if you dig in, you find that most of those come from libraries that are written in languages where the compiler does not have this hardening feature implemented. Most specifically, currently not yet fully implemented in the Rust compiler. But I also saw examples with Haskell and Go code, and probably for other languages, you might find something similar. I also found one or a few libraries where, there's a distro-wide default of this flag gets enabled everywhere, but then there's maybe 1 or 2 libraries where that default doesn't get propagated through properly entirely, and so you don't get the hardening that you thought you would get. And then, yes, it also highlights a few assembly-written code where implementers like, oh, yeah, it's not implemented here, but it highlights, so the scanner does find those. And there's still also a few false positives. Just the example on the code, so that break instruction stops regular control flow. And it turns out that compilers, when they know there's that code here, they go and optimize and they remove pointer authentication instructions, and so the static analyzer has to detect these to not report false positives. So the conclusions, I think, are for just this pointer authentication, yes, it is possible to implement it. The cost of doing so is very reasonable. The cost of running the analyzer is very reasonable. The diagnostics coming out are actionable and useful. And there's still a bit of work to make it production quality. But remember, like, this was the one that I thought was easy to implement. Let's now go to the one that I thought was hard to implement, stack clash. Again, I'm going to try to very hand-wavy explain roughly what stack clash is all about. So assume you've got the program something like this. That last access to the array A might get translated to an instruction like this. Basically, you load it from the basis stack pointer with some offset in the register. And that offset might be loaded from memory, the array A lives on the stack. Typically on the stack, I don't know all operating systems, but some popular operating systems have guard pages. So if you go beyond the stack, the operating system will detect that you're accessing just beyond the stack. But if this, like the value in that register would be attacker controlled, then maybe they put in a value that's huge and like you jump over that guard page and undetectedly they end up loading something from the heap or from some other memory region. And you could have similar issues with store instructions also. So how can you protect against that? So that's where the stack clash protection hardening scheme, which has been implemented over the past couple of years, comes in. And the idea is when we grow the stack, we only grow the stack one page at a time. And before we grow it by another page, we make sure there's definitely a memory access in between. There's a lot more details, again, on this blog post I pointed to earlier. So if we wanted to check that these properties were present in binary, what would you have to look for? You would have to look for what are all the stack pointer changes. And you would also have to be able to detect all the access to the stack because you need to check, like, was there an access between two stack pointer changes? I'm just going to show, like, again, implemented this in this iterative way. You look for all the false positives. You look, I'm not detecting this pattern. So what are the kinds of patterns that you need to detect? Very hand-wavy. This is the kind of stack protector loop. So you're incrementing page at a time. And so typically you get a loop in your prolog somewhere. What are the kinds of patterns you need to detect there? Well, here the data flow analysis needs to track what is the known maximum value of a register, like that sub instruction at the bottom of the slide decreases the page, and by some register, and you have to know it's at most one page. The stack pointer itself can be spilled. And so you have to detect like when that's filled or loaded again. Oh yeah, that was pointing to the stack. Sometimes constant values are put into registers and then you change the stack with that value from the register. So you also need to track that. Sometimes, as I said before, you have dead code in your binary and somehow your static analyzer has to detect that too. Otherwise, you also get false positives. There's a typical code pattern for when a stack pointer gets aligned. So you also need to recognize that you're masking off with some constant and then you're still within a page. Very hand-wavy here. So what is my experience implementing a prototype here? Well, it was also implemented using the data flow framework in Bolt, at the same way as a pac-ret scanner iteratively, just trying to reduce the number of false positives. This work, again, not fully finished, but at the moment, I'm still currently getting stack clash gadget reports on 39 out of the 2,000 libraries that is being scanned. I see a few more patterns there that need to be implemented. analysis speed as fast as pac-ret, even though the analysis is a lot more complicated. Implementing it so far about 1,000 lines. Conceptually more complicated, but still doable, I think. I thought, okay, I'm still seeing quite a few gadgets getting reported, but presumably a lot of false positives. How do I know if this scanner actually could work? Oh, let's test on a smaller test suite. I built the LLVM test suite with GCC. I picked GCC because it has implemented stack clash protection for a longer time. It only landed in LLVM very recently, for AR64 at least. And there it sees like if you build the test suite without stack clash protection, it finds 101 gadgets. With stack clash protection, it finds just one gadget, where for that one gadget, it takes a little bit of time to analyze in detail, like, is it a true positive or a false positive? I'm not fully sure just yet. But I think this gives an indication of, like, there's something here. It seems possible to, like, for the far majority of programs to be able to analyze, this is how stack movement happens. So there's still a bit of work left to implement a few more pattern recognition things in the analyzer. So let me see. Let me try to summarize all of that. It was really a really quick way through some of the work here. So what have I talked about in all of this? Maybe the main takeaway might be, I think that security has become a third pillar of compiler design and implementation, and it isn't going to go away. I also talked about it is not that easy to test security hardening implementations. And we've got some evidence of that by getting issues getting reported on. There are gaps in the implementations. So next I wondered, like, could we create a binary analysis tool to help build better implementations? Reusing Bolt, because that creates a win-win situation with the optimization use case. And so far, my general experience is, yes, it's absolutely doable to build a scanner for pac-ret. Most likely doable for stack clash, still a bit more work needed. And so presumably also doable for a lot of other hardening features. So and there's a lot of value in having a scanner like that. So yes, by now I'm convinced, absolutely, we should build such a scanner. Such a scanner, just reiterating, can be useful during compiler development, integrated in continuous integration to avoid regressions, maybe integrate with fuzz testing to find more problems. It can help with better checking that a hardening feature got applied correctly across a whole distribution. It could also be a useful basis for other binary stuff you want to check in an implementation. One example, correct frame chain creation, probably there are more examples. There's the prototype I talked about here. It's available on the branch. The link is on the slides. There's also an RFC that I posted last week. And maybe the most important part, like if you think this is something that should be created, then please reach out. Please leave your comments on the RFC or just at this conference, come talk to me. Or just online. I also have office hours. Like you can find lots of ways to reach me. And please tell me you think this is a good idea. And even better, provide feedback or even like help with implementation work. Thank you very much.
Thank you, Kristof. We have time for some questions. There are microphones in the aisles, or I can also bring the microphone to you.
Thank you, Tanya. Thank you, Kristof, for inspiring talk. An obvious question. Have you considered implementing in Bolt not only checks for security hardening inserted properly, but actually inserting security hardening in Bolt? This way you can cover Go, Rust, and all the languages that don't have it yet.
Yes, absolutely. So to just rephrase the question, why don't we just implement the hardening in Bolt and then like every binary?
Maybe it's impossible.
Yeah, yeah. I've considered it for like a split second, and then I think it's impossible to implement most hardening features. Well, in general, it's impossible for all hardening features because some of the hardening features take in information from the source code. Like, just one example, if you apply pointer authentication to all code pointers, typically the way you sign pointers is dependent on some information from the source code, like the type of the pointer. So for some hardening features, you need information from the source code. But it might well be possible for some hardening features. I'm not entirely sure.
Any other questions?
Hi, thanks. This was amazing. So on slide 25, you say these are the key takeaways and the important parts that people should consider. But I think one of the key aspects where you say, you know, we should have some common framework to test these hardening features. That would also be a little bit inclusive to the security researchers, because instead of only issuing a paper, they also can like have a tool to extend it so that, you know, they protect it as part of the work. But my other question was,
Maybe I'll just say like, great, thank you. I've got one more reason to say like this is a great idea.
my question is, since Bolt can optimize and change the binaries, if you implement the analysis there, can there be an exploit actually if you run and test your hardening features to change the binaries so that you introduce some? Because you have like a infrastructure that can change the binaries.
So if I understood the question correctly, like Bolt can rewrite binaries. So could there be like a malicious backdoor injected into Bolt that rewrites the binary and injects a backdoor that way? Yeah. Yes, at least theoretically, and maybe practically. I think that's like from a theoretical abstract point of view, that's no different from a backdoor in the normal compiler code generator or the mid end or the back end. It's my best guess. I haven't thought about that. Maybe there are more specific aspects there.
Looks like we got another question. Make his way up to the mic.
Hello, Jogo from Kari. Thanks for the talk. I was wondering, does this hardening features impact anything? How many the chain performance? Why do not usually use everywhere? And if they do impact performance, could you use both to identify places where you actually need to do hardening instead of doing everywhere?
So yeah, the question is, do hardening features in general affect performance? And I think, well, the answer is yes. How much it affects performance, that really depends on the hardening feature. Like it goes from hardly measurable to like some of the ones that only get used in very niche use cases, dozens of % sometimes, if you really care. And then the next question is, could you use Bolt to optimize away some of the overheads from hardening features? I haven't thought about that, so I don't know. One thing that immediately comes to mind is, if you do so, you'd better be sure that you don't accidentally drop some of the security hardening features. So maybe like having the scanner to still scan, like, do I still have the properties after optimizing here? Would actually be helpful to start implementing some of these optimizations where you really want to make sure you don't accidentally leave a gap in the hardening. Maybe that's the start of an answer.
Hello, Kristof. Thank you for the talk. I would like to ask if you, while developing the scanners, if you've taken any inspiration in like the long history of like binary analyzers and binary analysis platforms from the security researchers and vulnerability researchers.
So I did look around for a number of different binary analyzers to look for, like, where could I implement this? In the first prototype, I used the Anger framework. That pac-ret scanner first got implemented in the Anger framework, and I found that it didn't support some of the newer ARM instructions, where newer was really like introduced in the last 5 years. And that's where I thought, like, yeah, it's good to implement a prototype in this framework, but then if I want to make sure that this can be used to be like scanning whole binaries on newest releases of distributions, which presumably are going to use newest instructions, maybe I'm going to need a framework that's a bit more like industrial or production quality, or maybe not a full academic project. And probably there are also some scanners or binary analyzers like that, but like Hydra, or I think I've also seen references to IDA as an analyzer that's being used quite a lot by security researchers. My main observation there was these tools seem to be optimized to do like interactive analysis of one binary, where you really spend a lot of effort to try to reverse engineer what is this one binary doing. And it isn't really optimized for the use case where you're just going to batch analyze like a whole distribution or something like that. So I think you probably could implement it as something like Hydra, but if you already have a tool available that us compiler writers have access to, and it's already optimized for batch processing, lots of binaries, it just overall seemed like Bolt was a little bit better. But I think, for example, you could implement something like this also in Hydra.
Hi, Kristof. Thanks for a great talk. My name is Amir. I'm from Bolt team. I will just use this opportunity to, well, first of all, thank you for this important work, and I think it might be quite useful to the security researchers and, well, in general, taking Bolt to wherever we didn't envision it to be useful. But some of the questions are, I would say, more practical. What are the pain points that you experienced while building this tool? One specific idea is whether something like a data flow graph would have made analysis easier, or in general, what do you think we can do to make life easier for researchers who would want to implement this analysis?
So thank you for that question. A data flow graph specifically, I hadn't needed for these two analysis I needed to. Maybe I needed it for some other analysis. One thing I did end up implementing is because for Stack Clash, I had to implement quite a few different data flow, like what are these equations called in data flow analysis theory? There's probably lots of people in the room who know that better than me. But I had to implement quite a few analysis where basically you have a lattice structure, like you go bottom, top, and you have some specific value. So I implemented some framework to be able to reuse that, like on top of the data flow analysis, have a lattice class that represent, and then it becomes easier to implement. But these are really small additions. Is there anything else I thought of? Not really anything huge. I think maybe the biggest thing would be, as one of the co-donors, please accept these contributions. Thank you.
All right, that's about all the time we have for today. We're going to now have a 30-minute break in the foyer, but let's thank Kristof one more time.
Thank you.